Okay, welcome to the chapter 4 for the aromatic ingredient and flavors applications. Alright, so for this chapter 4, we're going to talk about the natural and synthetic flavor. Okay, so for this chapter, I'm going to divide it into two parts. Okay, for part 1 and part 2. So for this week, we're going to talk about part 1, which is the extraction of natural flavor. Okay, so let's look at the natural flavor. Usually they are from plants. Okay, so from plants you actually extract the natural flavors out for use in the food. Okay, so there are about 2,000 to 3,000 different flavor chemicals are used in the commercially. Okay, they are commercially divided into sweet and savory flavors. Usually, if you are looking at plants, okay, the natural flavor in plants actually is a major source of sweet flavors. And some types of savory flavors, such as vegetable and nuts flavors, but generally they are not a good source of roasted and meat-like flavors chemicals. But by saying that, usually if you have a further processing of these sweet flavors, okay, it is possible to actually further react into savory, okay, the flavor. Alright, so for examples, when cooked at high temperature, okay, especially in the presence of oil and fats, instances for like fried or roasted potatoes, okay, they will sort of like give the savory type of the flavor. Alright, so usually what happens is that all these natural flavors are introduced or you are incorporated into your food. Okay, then right after you incorporate it, usually there is a cooking process. So the cooking process will actually generate all these savory flavors. Okay, so you can see that a lot of the meat dishes, okay, you actually add these plant extracts, okay, and so you actually, when they generate all these savory flavors, it actually enhances the taste of the meat. Before I talk about the flavor extractions, okay, a few things that I need to mention, like for example, these words character impact flavors. So what is character impact flavors chemicals? Basically, it's a single flavor chemical that gives an impressions that determine the perceived identity of any product containing it. Okay, what it means, right, is like for example, vanilla beans. Vanilla beans inside, there are a lot of flavors chemicals, but the one that is considered as a character impact flavor chemical is vanillin. So for example, if I give you extracts that is only has vanillin, you can, when you smell it, you can straight away determine that is vanilla flavor. That is what it means by character impact flavor chemicals. Okay. To add on that, the character impact flavor does not necessarily have to be a low threshold of perceptions. Okay. What do you mean by low threshold of perception? Means that it can be detected at low concentration. Okay, not necessary. Yeah. So, for example, the alpha fluorescents, okay, which is the character impact chemicals of dill, right? You require high concentration in order to perceive the dill flavor. Alright, so you require high concentration. But by looking at it also, right, is that in dill itself, okay, in dill, the chemical, okay, is in rather high concentration, and there's no other flavors in dill that can compete with this dill flavor. Yeah. Alright, so the character impact flavor, as I summarize, okay, it can be a low threshold or it can be a high threshold perception chemical. If you're looking at the flavor qualities, usually you only need a very little, okay, in order to incorporate into the food. Yeah, the concentration rarely exceed 10 to 50 ppm. Okay, in other words, it's about 0.01 to 0.05 gram per liter. That's very, very little, yeah. Okay. Some flavors, right, once they're extracted, they actually, before they supply to the consumer or to the commercial, they can be diluted. Okay, it can be sell as it is, the extract, or it may be diluted for certain food application. If you want to be diluted, okay, it needs to be diluted in a food acceptable solvent. One of the very common one is propylene glycol. Okay, sometimes you can dilute in ethanol. Okay, or it can be diluted with a bulking agent like maltodextrins, or even the microencapsulated. Yeah, this one is microencapsulated. Usually is a bit of a protective effect, which means that it protects the flavor from degradation. Yeah, usually is from oxidation. Okay, so it can be diluted. For this, actually, the diluted versions, right, usually is for the consumer. If you want to sell to consumer, they do not want to be so concentrated. Okay, they can sell in the diluted versions. So it can be easier for them to incorporate to their recipe. Okay, and actually depending on the solvents, okay, or the different medias, it actually can impact on the perceived threshold. Yeah, okay, so even though you got the same chemicals, but depending on the different type of the media, okay, it actually can impact on the perceived flavors. So be extra careful, okay, of what kind of medium that you are using, yeah, to dilute your food solvent, yeah. Even though it's the same concentration, but the perceived is different. Okay. The flavor molecule can also have some other functional effects, yeah. Okay, some flavor, not all of them, but some flavors, yeah. Like for example, it can give you certain type of desirable color, like the turmerics. Okay, turmeric can be a bit orangey yellowish. Okay, can be desirable, can be undesirable as well. Sometimes it can has the antimicrobial effect or antioxidant effects. Yeah, all these are the plus point. Okay, which means that in addition to the flavors, it actually give you antimicrobial, antioxidant activities. So these can actually help your products. Okay, it can be a selling point as well, which means that you say that it has been added this. Okay, it has antibiotic effects. Okay, it's good for health and things like that, or it has antioxidants and etc. Yeah, so you can use all this as a selling point, as well as you can actually use these to actually protect your food ingredients. Okay, whatever you put inside, you can use it to protect as well. But you really need to decide whether the concentration you added inside have this kind of impact. That is another case. Okay, because as I mentioned, it's quite low, the concentration you added inside. So whether if you provide the antimicrobial or antioxidant activity, that is another case. Yeah. Okay. Okay. So the perceived quality and sense of flavor also depending on the media, temperature, and pH here, which means that it really depending on your recipe as well. Okay, what temperature you are serving, what is media is it in, okay, what kind of pH is in your recipe as well, right? And they also found that the protein concentration can actually affect the flavor components, yeah, the volatile components. Okay, with the presumptions that it could be because the protein molecules. Same goes to fat. Okay, if your recipe has a high fat content as well, okay, it can affect the perceived the flavor, because it can have these partitioning effects. Yeah, all right. Provided that if just say that, for example, your flavor components is very non-polar, okay, is non-polar, and what happened is that it could possibly bind to the fat components and is not releasing out. Okay. Before that, okay, the head space, what I mean by head space, okay, over here, head space means that when you have a liquid, okay, the volatile flavors that actually releases to this area is what we call the head space. Okay, so usually the head space is basically those that we can smell. Okay. Okay, this is the process of the natural flavors, okay, extractions. The flavor extractions is usually from plant, as I mentioned, okay. So from plants, you can have a different type of use a different type of the extraction methods, like for example using the solvent extractions. Okay, I will mention a bit of this later on. Using a solid phase extractions, solid phase micro extractions, steam distillations, supercritical fluid extractions, microwave aided extraction, and ultrasound aided extractions. Yeah, so you can use a different type of the extraction methods. The extraction methods, right, is really depending on the types of the material as well. Where is it located? Where's the flavor chemical located? And also the property or the chemical structure of the flavor molecule as well, or the flavor chemical as well. Okay, because depending on what kind of, like for example solvents, what kind of solvents you need to use, okay, depending on whether the solvent can actually dissolve the chemical molecules. All right. But for this lecture, I will going to concentrate on this, what we call the super extractions. Okay, before I talk about this, I'm going to talk about the solvent extraction first. Then after that, I'm going to talk about the supercritical fluid extraction, which is the enhanced version of this solvent extraction. Okay, because what happened is that this supercritical fluid extraction, right? Okay, there are a lot of research going on with this one. Okay, and is one of the very effective, okay, as well as is very gentle to the chemical molecules, okay, as well as environmental friendly. Yeah, so I'm going to emphasize in this one. Okay, all right. Once you have extracted the flavor molecules, then the next step, right, is really to determine, okay, using the gas chromatography mass spectrometry analysis, okay, determine what kind of flavor components are in there. You can use either the GCMS, okay, combination of the gas chromatography, which is in a gaseous state, okay, and then this is actually measure the mass of the molecule. Okay, so the molecule are separated using the GC, okay, gas chromatography, and the will be analyzed. The mass will be analyzed by the mass spectrometer. Okay, you can actually use the GC olfactory analysis as well, or you can combine these two. Yeah, the olfactometry analysis, right, is basically using the nose to determine what smell is it. Okay. One is separated, you can smell. I'm going to talk more about this one in the later slides. Yeah. So once you have done the analysis, you can confirm the flavor. Okay. So this is the natural flavor extractions method. So as I mentioned, it really depending where is the location of the flavor chemicals or flavor molecules. Okay. If it's you need to actually disrupt the area, okay, or the structure of the plants. You can use a mechanical like grinding, okay, cutting and so forth, okay, or blending and so forth. Mechanical using thermal heat, okay. Usually heat is not really that advisable, okay, because a lot of the molecules are heat sensitive. But in some cases, heat is preferred as well. Like for example, if you are cooking curry and so forth, you will actually fry a bit of the spices to release out the flavors. Yeah. Okay. You can use enzyme to break down the structure. to release the flavor and the aroma chemicals containing the cells here. If you're looking at the plant cell walls, the plant cells are structure as well, you can see that they have the middle lamina, okay, between the cells, okay, the gap between the cell, they could be as well, or it can be inside, okay, at the secondary cell. Alright, so it really depending on where is it located. Usually you can use these three methods to release out the molecule before the extractions. Alright, so one of the examples is pandan leaves. Okay, pandan leaf is made of the cell structures. Okay, usually you get boiling, it can release it, but a lot of them are being released out. Yeah. If you are looking at something else like the pepper berries, okay, the pepper, the peppercorns, okay, it's a very different structure, yeah, compared to the cell wall. Okay, I'm going to discuss it later on in the next slide. Pepper berries exist as fully ripened, okay, which is red. Like look at this, this is a ripened one, or the unripened, which is green color. Okay, green is unripened. For the ripening one is it will change color, of course, to red color, and their flesh will become softer. Yeah. So once the berries are hand plucked, okay, the ripened one will be processed to white pepper, okay, and the unripened one will be sun dried to produce the black pepper. Black pepper usually the taste is a bit stronger and more pungent, okay, compared to white pepper. Yeah, so it has been differently used as well. Okay, that's why there's a white pepper and black pepper. Yeah. If you're looking at the structure, okay, it's very different. Okay, it comes from the berries. Before you actually go for extraction or use it as a peppercorn, okay, you will remove this layer, okay, the pericarp layer. So this pericarp layer will be removed. Alright, so what happened over here, right, is that, okay, just to repeat what I have mentioned here, okay, so the piperine, okay, piperine is what the flavor of the pepper, okay, the what we call the character flavor, okay, the one that we have mentioned before, okay, the character impact flavor of pepper, okay, this one. So piperine is very crucial, okay, and most of this piperine is located here. So the pepper flavor, the pungent and the flavors, right, is attributed to the piperine, which is located here, as well as the essential oil outside here. Alright. So in order for you to extract out, so you will need to have this outer layer removed, okay, leaving the essential oil and the perisper. Of course, you will break it. You can actually use the solvent extraction method. Yeah, solvent like for example ethanols, okay, acetone, ether, dichloroethane, and so forth. Yeah, all these solvents. If you're looking at the structure, yeah, just go back one slide. You can see that it's rather quite with the ring form. Ring form usually is the non-polar. Okay, so you can see that most of it, the solvent here is the non-polar. Okay, even ethanol also got the non-polar ends, which is able to dissolve it. So you can use the solvent to extract again and again. Okay, so what happened, right, is that you put the solvent with the crushed pepper, okay, or peppercorn, crushed peppercorn, and then let it dissolve the flavors. Then after that, you go under the reduced pressure, okay, you reduce the pressure to actually evaporate the solvent, okay, but the flavor component is too heavy, it won't evaporate. Yeah, okay. So then after that, you put in the solvent again and repeat the process. Okay, so what happened, right, is that you get a concentrated extract, what we call oleoresin resin. Okay, oleoresin resin is the concentrated material, and it's very viscous. Okay, and usually is about 5 to 20 times stronger in flavor than their corresponding spider, which means that it's very concentrated. Okay, example is here. Yeah, oleoresin resin is very dark color of the peppercorn. Okay. Okay, before I go on, okay, Why do I highlight this reduced pressure? The reason is that with the reduced pressure, you can evaporate, okay, the solvents without increasing the temperature, which means that it's good. Okay, which means that you can preserve the quality of the peppercorn, okay, or pepperine. You can preserve it, okay. So because the heat can destroy the components here. So typically the oil resin, right, contains about 15 to 20% volatile oil and 35 to 55% of pepperine. Yeah, so it's quite concentrated. Okay, just very little. You can just add a very little of this oil resin into your food components. You can taste it already. So this oil resin, okay, very similar with the methods that I have mentioned there using the solvents. You can also do it to other type of spices, yeah, like basils, okay, capsicums, cardamoms, okay, celery seeds, cinnamon bark, clove bud, fenugreeks, okay, the fir balsams, okay, ginger, jumbo, and so forth. You can use it on different type of spices using the solvent extraction methods. Okay, so once you use that, okay, dissolve and again, okay, you will form an oil resin, okay, and the oil resin can be used to the food. Okay, here comes to the point, yeah. The solvent you use, right, you can use the non-aqueous, okay, type, okay, which is non-polar, okay, or you can use the polar, like alcohol or the carbon dioxide, yeah. So you can use the different types to actually extract out. Alright. The one that I wanted to really introduce is actually what we call the supercritical fluid extraction methods. Normally, traditionally, you can use, for example, all those different types. Again, not only solvents, yeah, you can use distillation and so forth. But usually, using all these traditional methods, right, including using the solvents, okay, all those what we call the non-polar solvents, okay, that I mentioned before, like the sorry, for example, like using all these acetone, ether, and so forth, okay, all these are a bit. Sometimes it can be toxic as well, okay. First is that it can be toxic, okay, if you use large amount and if you didn't remove all of them, okay, and usually have a longer extraction time. Sometimes also comes with a lower efficiency, which means that you cannot fully extract whatever's in there. And the solvent sometimes can pose as an environment pollutions, okay, and sometimes it can degrade the thermal label components, which means that it's sensitive to heat, yeah, okay, because if you use a distillation, okay, the heat will be involved and it can destroy some of the components. You can use, okay, so alternatively, which is quite popular nowadays, you can use what we call supercritical fluid extractions. Okay, so for this, right, is exactly like the extraction methods, but instead of using the those ether and so forth, okay, you're using carbon dioxide. Okay, carbon dioxide can reach to if you tune the pressure and the temperature, you can tune to what we call a supercritical stage. All right, so using carbon dioxide, you can extract in the more quality, okay, actually can have a better quality extract out from it, okay. So it's exactly same as that, okay, just that you are using a different type of solvent. In this case, we use carbon dioxide for this supercritical fluid, yeah. The carbon dioxide can go for this, that's why we can call it as a supercritical fluids, okay. It provides a higher selectivity and shorter extraction time, okay, higher diffusivity and lower density, viscosity and surface tension than traditional solvent. All these give you a better penetrations into the cell structure to extract out the flavors, okay. And carbon dioxide can be considered as safe, non-toxic, non-flammable, non-explosive, and sometimes it's quite economical, yeah, because you can just get it out from air, okay. easily available and can be removed from the extracts. Okay, let's look closely to what is supercritical fluid. Okay, supercritical fluid extract is the use of a gaseous medium that is in the state above its critical temperature and pressure. Usually when we talk about that, we talk about what? We talk about liquid state, solid state, gaseous state. But this is a different state, which is what we call the supercritical fluid state. Yeah. In this state, right? Okay, for carbon dioxide, is most commonly used as a supercritical fluid. Of course, there are other materials that can go into this supercritical fluid stage. Okay, but carbon dioxide is one of the very popular one for these extraction methods. Okay, because it's quite easy to attain the critical temperature, which is about like 31.1 degrees Celsius at the pressure of 7.39 megapascal. Okay, you can actually get the carbon dioxide into a critical fluid stage. Yeah. When you reach these supercritical fluids, actually you will have this stage here, which is the liquid and the gaseous state. Okay, so it behaves in these two stages. It behaves a bit like a liquid, it behaves like a bit of a gaseous, yeah, in this supercritical fluid stage. Yeah. With these dual characters, yeah, it makes it a very, very good extractants, okay, that possess the solvent strength, okay, and density of a liquid, along with a high diffusivity, low viscosity, and surface tension of a gas. So it can penetrate into the cell material, the cell structure material, okay, and extract out the flavor components. Okay, so it's very interesting over here. Yeah. Because CO2 is non-toxic, non-flammable, low cost, so industry love to use carbon dioxide. Yeah. So however, carbon dioxide is a non-polar. Okay. It really depends. Depending on the flavor chemical structure. Okay. If you just say that your flavor chemical is a polar, then the carbon dioxide may not be optimal. I won't say it won't extract out. It won't be optimal to extract the polar flavor molecule. So in that case, you actually can add a core solvent, okay, like a alcohol or water to be a supercritical fluid. Okay, so you can use it by alone, okay, carbon dioxide alone, or you can add additional fluids, okay, to extract together. Okay, if you just say that your components, your flavor components is have a polar structure, okay, you can add others as well. Okay, so remember, yeah, the flavor components are not just one. Yeah, okay, there are a lot. The character impact component is just one. Okay, but it will come along with a lot. Like for example, vanilla beans. Okay, vanilla beans, right, inside contains a lot of different type of flavors. So when you use just vanillin itself, won't be that fulfilling. The flavor won't be that fulfilling or that full, okay, compared to using vanilla beans. Okay, that is what I'm trying to say. Okay, so this is how the equipment are being installed. Usually, you can see over here, this is the extractor. Okay, so you put in your raw material here, and then you will have your CO2. You will go through the heat exchanger, and the pressure, the pump here is to pressure it to get the CO2 into the critical fluid stage before it go into the extractor. Okay, so one is inside, then if you extract, and then it will be removed. Okay, it will be removed into the separator, into an extract tank. So here is the extract out. Of course, it can redo again and again. Okay, so you can see from here, it can go back into the extractor, and then your raw material can extract the material from the raw material again and again and again. Okay, in this case, you also, once it's concentrated enough, you also can produce what we call oleo resin. Okay, oleo resin. Okay, it's a concentrated the flavor extract. Yeah. All right. For example, you can see from here, ginger, okay, you use 25 to 30 kilogram of ginger, dry ginger. You can use the supercritical CO2 to extract about 1 kg of ginger oil resin. You can see from very thick, very concentration. So every gram of this, you can actually replace about 30 gram of dry ginger. So it's quite a lot, okay. Just a few drops is like, wow, very strong, okay. Commercial products love to use this, yeah, okay, because one thing is that transportation fee. If you buy this from the supplier, transportation fee, you can save a lot, and also the dilution effect to your recipe is going to be very little as well, which means that you still can retain or adjust your recipe accordingly, okay. See, very strong ginger taste, okay. Spicy, fragrant, soluble in most of the organic solvents, okay. Volatiles components very concentrated, yeah, and the density is slightly more than the water, so it's heavier than water, yeah. So if you look at the so all this, yeah, if you look at this, please refer to the chapter 4 handout 2. Okay, again, this journal is very good. It talks a lot about this supercritical CO2 in using it to extract plant material. Okay, please read this. And in this company, okay, this company RAPS from Germany, okay, this company is in Germany. It has a lot of flavor extracts, okay. You can look in their company profile here, as well as please look at their brochure, chapter 4 handout 3, okay. There are a lot of flavor over here, and the technique they use is actually using the critical fluid CO2 to extract all the flavors out here, okay. The flavor can be in the liquid form, can be in powder forms, okay. Can be for the taste as well as the aroma, yeah. Okay, so for the gaseous one, for the aroma one, okay, once you have the extract, if you want to determine the aroma actually sometimes is quite sensitive here, okay, because you cannot smell. You can taste quite well, but you cannot smell, okay. Aroma you can determine using the GCMS. Of course, the taste you can use mass spectrometer, HPLC, okay, high performance liquid chromatography to get the flavor component. But for the aroma, you need to use the gas chromatography olfactometry, or you in combination with the mass spectrometer, yeah, okay, the one I told you before, which means that you put this into that, okay, you make the you add a bit of heat, okay, to make it volatiles, and then you separate using the column called the GC column, okay. Once you separated, okay, you can see there are different type of peaks over here based on the different type of mass of the molecules, and then you can smell it as well, okay. So it sort of like correlation between the smelling and the GCMS. Then you can identify that, oh, this peak is what molecule and give you what kind of smell, this and so forth. This is really to confirm that the aroma compound or the molecules is in your extract, okay. Okay, let's look at this video here. Let's talk about the extracts here. Oops. Okay, so just now that video is not really analysis of the flavor extract, but it's a demonstration of how the GC olfactory methods can use it to determine their flavor compound. Okay. Okay, so when you're looking at this, the odorants, okay, or the volatile components, okay, if you're looking at just the black tea, okay, there are a lot. You see, it can contribute, have a lot of different molecules that contribute to different flavors. So all this overall, depending on their concentrations, it gives you this the overall odorants from the black tea. All right. So same goes to cocoa mass. Okay, the smell comes from here. Different type of the molecules. Alright, of course, again, it depending on what is the individually, what is the concentration of it. If you contribute to the overall, the smell or the volatile smell from the product, again, from the ingredients. Right? Okay, just to summarize the part 1, okay, so for the plant raw material, you can use the traditional extraction methods, okay, or using the modern methods here. The one that I really emphasize is using the liquid CO2 extraction, which is the supercritical extraction methods, okay, is one of the best one. Once you get the extract, then you can apply directly into your food components, okay, or your recipe or your food product and so forth. You can use it and generate the desirable flavors, or okay, you can actually, for example, you can further generate the taste and smell, okay, through, for example, in here, this is the concentration. You can concentrate further, or you can dilute and so forth here, okay. This is the one that is very critical, which means that the flavor component in the extract can actually form certain type of flavors, okay, in addition to the extracts here, which means that extract already got the flavors. Under the heat, it actually generate more new flavor components, okay, like brewing coffee and so forth. Then you got more aroma coming out, okay. Or the extract can be added into, like, for example, meat and so forth, okay. Then what happens is that undergo fermentation, it can actually generate more flavor out, okay. So that is what we have mentioned before, flavor generations, okay, which means that you have a certain precursor, okay. The precursor, if you undergo like heat treatments or give it enough time for it to react, okay, to give you more flavor components, okay. So you can do that as well as you can directly use the extract into your recipes, okay, or add directly into the food and so forth, okay, without the extract, without the further development of the flavor as well. So you can really, depending on what you want to do, okay, depending on what kind of product as well, okay. Alright, so remember to actually write, okay, to indicate in the palettes, okay. For this time we don't have activity, okay, so make sure that you actually indicate, okay, in the palettes whether you got question or no questions, okay. It's very important as well for me to mark your attendance here, okay. Please remember to do that. Thank you.